Hello all, myself Professor Kishan GS, working as Assistant Professor in the Department of Mechanical Engineering, Maharaja Institute of Technology, Mysore. So I'll be handling the subject called Material Science with the code 18ME34 along with my co-faculty Professor B. Harish, Associate Professor from the Department of Mechanical Engineering, MIT, Mysore. So in this particular session, we are going to cover the extended part of mechanical behavior in material science, what it has been covered till the last class. So to have a brush up on that particular content, so we know that the mechanical behavior of materials is studied under two regions. One is elastic region, other one is plastic region. So to be very specific, elastic region is the range in which the materials upon unloading the loaded condition, it comes back to its original condition. If the material is loaded beyond the elastic limit, wherein the material cannot come back to its original shape and size, then we are going to say the material lies in its plastic region. So coming up with this elastic and plastic region, we do have two concepts as well. In elastic limit itself, we have linear behavior and non-linear behavior. So the linear behavior is accountable when the stress is directly proportional to strain. So when the curve, whatever we have studied in the previous session, the limit wherein it shows that the stress is linear to strain, then the properties which could be defined in that particular limit is called as linear behavior or linear properties in the elastic limit. Whereas in this particular session, we are going to deal with specifically the non-linear elastic behavior and properties of the material under mechanical behavior topic. So what is meant by non-linear? So the term non-linear itself defines that here the stress and strain, if we go with the condition, it will not be proportional to each other. At that particular point of time, how we define the behavior of materials is categorized under three terms here. One is secant modulus, tangent modulus, and the last one is resilience. So we are going to deal with each of the topic here. First, we are going to take the secant modulus. So the reason behind identifying the secant modulus is that in non-linear proportionality limit with respect to stress and strain over a material, so it is highly impossible to identify the stiffness. So at that particular condition, when we are not in a position to identify the stiffness, we are going to define a term called as secant modulus. What is the secant modulus? It is defined as the average stiffness between the origin and any given stress. So you can just refer this particular stress versus strain diagram here. So here what happens, the curve represents non-linearity between stress as well as the strain. So hence what we are going to do, we are going to define a secant modulus which defines the average stiffness when the material is considered in the non-linear behavior. So here we have considered this particular non-linear curve against stress versus strain here. The slope what we have taken here represents the d sigma by d epsilon, wherein the sigma is represented to be sigma 1. That is, sigma 1 is nothing but any given stress considered in this particular region. So the secant modulus is defined by E secant, SEC represents secants, is equal to sigma by epsilon, where sigma is equal to sigma 1. So we have to always remember this. Sigma is nothing but the sigma which is corresponding to a particular point up to which we are going to define the average stiffness of that particular material. So this is secant modulus. Moving on with the next parameter, it is again tangent modulus. What do you mean by tangent modulus? Again, the reason behind identifying tangent modulus is that so we don't have any proportionality limit. So we have to define a parameter. So how we define tangent modulus is that it is the slope of the tangent drawn at any point. The point can be even considered as stress on the nonlinear curve, which means to say that the term tangent modulus will gives us the instantaneous stiffness of a material at any given stress. So here again in the same nonlinear behavior of a material with respect to stress versus strain, so wherever we draw a particular tangent, that particular tangent will be taken into account to draw this slope which gives us the instantaneous stiffness of a material where in the material is non-linear in its behavior. So here whatever we define, it is the definition of a material in the elastic limit itself. We haven't taken the material to plastic region. We are still in the elastic limit itself. In the elastic limit, when the behavior is non-linear, at that particular point of time, to identify the instantaneous stiffness, we are going to draw a tangent, and the slope drawn with respect to that particular tangent results in the tangent modulus. And this is the identity parameter for tangent modulus. E tan is equal to d sigma by d epsilon, wherein sigma is equal to sigma 2 here. So the definition of sigma 2 is nothing but a point wherein which we are identifying we are locating the tangent over the nonlinear behavior of the material. And the last one is the resilience. We have defined the term resilience even in the linear properties in the elastic region itself. That is the capacity of a material to release the energy which is absorbed once it is being loaded in the elastic region. So here also what happens, the resilience will also be taken into account even in case of the nonlinear behavior. Though we have, we cannot come across the proportionality limit here, we are going to observe the area under the curve which represents the condition of a material once it is being loaded and once it is being unloaded. Here in this particular stress versus strain diagram, you can just observe the curve here. The curve that represents from the origin to the point A through 1 is the loading condition, and the curve which represents from A to the origin through the number called as 2 is considered to be unloaded curve, or the response of a material once the load is being removed. So here, since the material has the capacity to come back to its original shape and size, since it is in the elastic limit itself, though we don't have the proportionality limit which is being represented through the curve here, we are going to again define the term called as resilience, which is defined as the ratio between the recoverable energy and the energy invested in the material during the deformation. As I already said, the curve number 1 represents the energy, that is the load being applied onto a material to a point called as A here, whereas the curve number 2 represents the energy which is being recovered, or the capacity of a material to come back to its original position. So hence, the resilience in nonlinear behavior will be defined as the area under the curve 2, that is this particular curve 2 divided by area under the curve 1 into 100. It will be measured in terms of percentage. And this is the definition of resilience. So these are the three parameters that we are going to study, that we are going to assess when it comes to the nonlinear elastic behavior of a material. The next topic of coverage for today's session is on the mechanical properties in the plastic limit or the plastic range. So here you can observe in this particular stress versus strain diagram, so there is a certain limit up to which the material behaves as elastic, wherein it can be brought back to its original shape and size. After reaching a particular point, the material gets converted into plastic, that is, it enters into a region called as plastic region, wherein it cannot be retrieved back to its original shape and size. So now we are supposed to concentrate on the behavior of materials once it starts yielding, that is, once it starts entering into the plastic region. So we have different parameters here to be studied when it comes to the material in its plastic region or plastic range. So the first point is yield strength. So how do you define yield strength? Is that it is the stress at which plastic deformation begins without any appreciable increase in the load. That is the point at which the material enters into the plastic region, that is this particular point. The stress corresponding to this is considered to be yield strength, that is sigma y is equal to Py and Py divided by A naught. So Py is the load at yielding. Yielding is nothing but a point wherein the material enters into plastic region. So the unit of the yield strength will be in Newton per meter square. Moving on with the second parameter, that is called as offset yield strength. What do you mean by offset yield strength? It is defined as the stress corresponding to the intersection of stress strain curve and a line drawn parallel to the linear portion of the curve offset by a specified strain. So you can refer this, but in this particular diagram we have a dotted line, and this particular dotted line is drawn parallel to the linear curve. Okay, the line is parallel to the linear curve. So here, this particular linear curve is considered to be offset by a defined strain. Along x-axis it is strain. So the defined strain is been considered, which is considered to be the offset distance, and the stress corresponding to this particular offset line, which is parallel to the linear curve, is represented as offset yield strength. It is represented using the symbol sigma p. Moving on with the next parameter, it is called as ductility. So it is the ability of a material to undergo deformation under tensile loading condition. See, the material will be subjected to different type of loading condition. Once it is pulled apart, it is considered to be tensile condition. Once it is load is applied towards the material, it is considered to be under compression. So the ability of a material under tensile loading condition is defined to be the ductility. Usually when the material is pulled apart, there will be change in the original length of the material. So we are going to define the ductility in terms of percentage elongation. That is nothing but L minus L naught divided by L naught into 100. Here L is the length of a material after the load is being applied, whereas L naught is the original length of the specimen or the material which is being subjected to tensile loading condition. Moving on with next parameter, that is malleability. Malleability is nothing but the ability of a material to undergo plastic deformation under compressive load. So the difference between ductility and malleability is that ductility is defined under tensile loading condition, whereas malleability is considered under compressive loading condition. So here the ability of a material can be defined wherein it is converted into thin sheets. After application of load, a solid member can be converted into thin sheet, and that particular behavior will be a concept of malleability. Moving on with the next parameter, it is ultimate tensile strength. How do you define the ultimate tensile strength? So it is defined as the stress corresponding to a certain value of load beyond which the specimen doesn't take any load is called as ultimate tensile strength. Here in this particular stress versus strain diagram, you can observe the curve here, that is stress versus strain behavior. In this particular curve, there is a particular point mentioned here beyond which the load is decreasing, the stress is decreasing. Means to say that to that particular extent, the material do possess of accepting the load which is being implied on it, and after it has reached this particular position, the material will never be in a position to receive further amount of load, hence the stress decreases and that leads to fracture of the material. So this stress, which is correspondent to the maximum load to which the material can withstand or sustain, is considered as ultimate tensile strength, and it is represented by sigma suffix u. So it is again sigma u is equal to Pu by A naught. Pu is nothing but the ultimate load wherein the material can withstand, and A naught is the area of cross section of the specimen. The next topic under the mechanical behavior, wherein the material is studied in the plastic range, is the fracture strength. What do you mean by fracture strength? It is the stress corresponding to the load at which fracture takes place, which is designated using the term sigma f is equal to Pf by A naught, wherein Pf is the load that results in fracture of a material and A naught is the area of cross section of the specimen, and the unit is Newton per meter square. In this particular stress versus strain diagram, you can observe here, this is the point of fracture of a material once the load is considered to be Pf, and the corresponding stress is represented as the fracture strength sigma f. So the next parameter is toughness. So toughness is defined as the ability of the material to withstand both elastic and plastic deformation. So in other words, it is defined as the amount of energy that a material can withstand before fracture takes place. So based on the behavior of material, whatever may be the condition of load which is being applied on the material, the amount of energy wherein the material can absorb or withstand before the fracture takes place, that leads to a parameter called as toughness. Moving on with the next parameter, it is true stress. So the word stress and strain, what we have studied in the earlier classes, is defined as engineering stress and engineering strain, whereas here we are speaking about true stress and true strain. How do you define true stress? It is the ratio of load to instantaneous minimum cross-sectional area of the specimen. So it is the stress measured with respect to an instant of the cross-section of specimen. It is represented by sigma dash is equal to load, and A dash is the area of cross-section of the specimen at that instant. So unit is again Newton per meter square. Moving on with the true strain, it is defined as change in length to the immediately previous length of the specimen rather than original length. In engineering strain, we are going to define it using the definition that is ratio of change in length to original length. Whereas in case of true strain, we are going to define it as the change in length to the immediately previous length rather than the original length. So it is designated using epsilon dash is equal to ln of Li by L naught. So L naught is the original length, Li is the immediately previous length. So in the next class, we are going to study the relationship between true stress and engineering stress, true strain and engineering strain. Thank you. Hello. In the last class, we had studied the different properties related to the mechanical behavior of a material in plastic range. At the end, we have understood the concept of true stress and true strain. In this particular class, we are going to study the relationship between true stress and conventional stress, true strain and conventional strain. Followed by the session will be on the plastic deformation of material through slip and twinning as well as strengthening of metals. So first we shall take up the concept of the relationship between true stress and conventional stress. So we have defined the definition of the true stress and conventional stress in the previous class. Here, to derive the relationship between both the terms, we are going to take first the conventional stress, which is defined as load per unit cross-section area, that is P by A naught here. So since the volume of the material remains constant throughout when it is being subject to a particular load, what we do is we are going to take the relationship as the original area and original length in terms of volume to the area and length at any instant of concern, so that we are going to derive the relationship between true stress and conventional stress here. So we are going to take A naught into L naught as the volume of the material at original condition, and A naught into Li, so Ai into Li, wherein it is the volume of the material at any instant of consideration here. So upon further simplification, in order to define the term A naught here, so A naught can be taken as Li by L naught into Ai here. So using this particular equation as 2 in equation 1, that is substituting the value for A naught in equation number 1, we are going to end up with the term P by Li by L naught into Ai. So here we have defined the term, that is the change in length, okay, Li by L naught is equal to 1 by epsilon. The result being taking up 1 by epsilon is derived here in this particular slot. So I'll discuss the description of this particular consideration of Li by L naught is equal to 1 plus epsilon in defining the relationship between true strain and conventional strain. So on taking this, okay, so we also know that the true stress will be defined by sigma dash, it is equal to load per area at instant of consideration on that particular metal, that is P by Ai here. So substituting the value of P by Ai, that is true stress, in equation 3, we are going to end up with the conventional stress sigma is equal to sigma dash by 1 plus epsilon, that is P by A naught is replaced by true stress here, that is sigma dash. So upon further simplification, sigma dash will be equal to sigma times of 1 plus epsilon. So this is the relationship between true stress and conventional stress. We always remember true stress will be represented by dash, that is sigma dash, and conventional stress is sigma, so 1 plus epsilon. So here we are going to derive at a condition where true strain and conventional strain can be considered here. So again, when it comes to conventional strain, it is the change in length to the original length of the material which is subjected to a particular type of load. So here the conventional strain is represented by epsilon is equal to delta L by L naught, wherein delta L will be considered as the change in initial length to the original length. Once the load is being applied, say for example, once we are applying a tensile loading condition, the length of the specimen will always go varies. That is, the length will always be increased once it is subjected to tensile loading condition. So keeping that in mind, we can define delta L is equal to Li minus L0. L0 being the original length, Li is the length of the specimen at that instant once the load is being subjected. So thereby, further using this particular value of delta L in equation 1, we are going to end up with the equation epsilon is equal to Li minus L0 by L0. That is, upon further simplification, Li by L0 minus 1. So thereby, upon consideration of LHS and RHS, we are going to end up with Li by L0 is equal to 1 plus epsilon. So this is the value of 1 plus epsilon. That is how we have derived with the value of 1 plus epsilon, and this is how we have utilized the same value here in deriving the equation for conventional stress and true stress. So further consideration of the same derivation here. So in order to identify the true strain with respect to conventional strain, we are going to apply ln on both the sides. So applying ln, we get ln of Li by L0 is equal to ln of 1 plus epsilon here. So this ln of Li by L0 can be taken as the true strain, which is the measurement of change in length to the original length at the immediate instant of consideration or the previous instant of consideration. So this is the relationship between true strain and conventional strain. Now we shall discuss the topic plastic deformation in single crystal. So when the material is being loaded beyond the elastic limit, the material is said to be present in the plastic limit. So upon further increase in the load, the material fails in the plastic region at a particular point called as fracture. So here what happens, we are going to study different types of deformation that occurs when the material is in plastic limit. So the first one is plastic deformation by slip. So here what happens, we have taken the consideration of the crystal with a ideal arrangement of atoms here. Once the material is being subjected to a particular load, say for example, we have taken here the application of tensile load. These two arrow marks represent the outside pull on a particular material that results in the tensile condition. Once there is a dislocation being identified in the material when it is being loaded in the plastic limit, the deformation by slip is identified to happen or occur when a set or a group of atoms get dislodged from its atomic site and just forms the another set of arrangement. So you can just observe the figure here. The entire arrangement is for a single idle crystal here. Upon loading condition at a particular point, this particular group of atoms has dislodged its original position, and it has taken a step like formation, resulting in the next set of atomic arrangement in the idle crystal, and this leads to further damage for the material, and it leads to a faster collapse of a material upon loading condition. So since the entire group of atoms is forming another set of arrangements, hence it is said to be deformation by slip, and the plane that results in separation of one crystal into two crystal is always be considered as the slip plane. So here what happens in this particular case, whatever may be the load, that is tensile or compression, the dislocation of atoms will always be subjected to the shear loading condition which is applied on this particular slip plane. So this is deformation by slip. Next we are going with the second type of plastic deformation in a single crystal, that is deformation by twinning. So the major difference between slip and twinning is that here in case of slip, a group of atoms get dislodged along a particular plane called as slip plane, whereas in case of twinning, a group of atoms just go with the next stage of arrangement such a fashion that on either side of a twinned region, the arrangement of atoms looks similar. Means to say that if we take this as an ideal crystal which is subjected to a particular load, again we are going to take the tensile load of load application here on the idle crystal. upon loading condition after a certain stage, what happens is that there will be a movement of or dislocation of group of atoms in such a fashion that the atomic arrangement on either side of a region called as twin region will be identical. So means to say that one side of the atomic arrangement will not be disturbed, wherein there will be dislocation of the atoms in the ideal crystal in such a fashion that after going with excessive number of atomic planes, a particular arrangement looks like the identical representation or the twinned image of the original set of atomic arrangement onto the left side of the ideal crystal as per this particular diagram. Here, the plane that results in twinning of the atomic arrangement in the ideal crystal is said to be twinning plane here, and the region that acts as a connectivity between left and right side of the atomic arrangement that looks identical is nothing but twinned region here. So again, even in this particular case, whether it is tensile or compressive load, the shear stress which is being acting on this particular twinning plane in the plastic limit will always result in this type of dislocation of atomic arrangement in the material. So here what happens is that whether it is deformation by slip or deformation by twinning, this leads to failure of material at a very early instant. So in the next session we are going to deal with the strengthening of metals, which results in the aspects to be considered to overcome these type of deformations and dislocations. Thank you. The last topic in module 1 goes with strengthening of metals. So far we have studied different behavior of materials, that is properties under mechanical loading condition in plastic and elastic limit, followed by different types of dislocations as well as different types of diffusions. Now, in order to overcome or in order to reduce the movement of dislocation, we are going to concentrate on different processes that results in strengthening of metals. So as it is stated, strengthening of metals is directly related to retard the movement of dislocation in any materials. So here we have different types of methods to resist the dislocation movement. One such is strengthening by grain refinement. So we have studied something on grain boundary and grain size here in the different types of dislocation. So here what happens when we concentrate on reducing the size of grain, that results in better formation of grain boundary in any material, that results in the increased hardness and strength of a material and thereby reduces the movement of dislocation. So this is a concept wherein we target the reduction in the grain size so that the strength of materials is enhanced. Followed by the next method, that is strain hardening. So during cold working conditions, so all these types of strengthening of metals and all, we are going to study in detail in heat treatment of metals module, whereas here it is only the introductory phase of strengthening of metals. So in strain hardening condition, we can quote like this: during cold working condition, when the material is subjected to plastic deformation, some amount of work is stored as strain energy internally. This strengthens the material. When the material is subjected to cold working condition, during the loading condition on that particular material, when the material is subjected to plastic deformation, that is when the material is going with the deformation in the plastic limit, there will be some amount of internal stored energy in the material that resists the deformation to happen, and that is where it is called as strain hardening, that increases the hardness and strength of metals. The third one being dispersion hardening. So as the name itself says, this dispersion here, so we can quote the method of dispersion hardening like this: hardness and strength increases when the finely divided hard particles of second phase is dispersed in soft matrix. So means to say that when the finely divided hard particles of metal 1 is dispersed in the soft matrix, that results in the dispersion of material from one phase to the another matrix phase, such that it increases the internal strength and hardness of the material, thereby it reduces the movement of dislocation and increases the strength of material. The fourth one being edge hardening. It is also called as precipitation hardening. So it is a strengthening of an alloy resulting from precipitation of finely dispersed second phase supersaturated solid solution with age. Here, as the name itself is age here, this is a method considered over a very long period of time here in order to increase the hardness and strength of material. So here what we do is, we are going to strengthen the alloy resulting from the precipitation of finely dispersed second phase. Here again the same thing, when there is a mixture of the dispersed second phase of material over a period of time, when the material is subjected to certain passage of time, that results at a particular, that considered to be at a particular age or a particular duration, the hardness and strength increases on its own, and hence it is considered to be age hardening. And the last type method is phase transformation hardening. Here what happens is that when a material is considered at different combination, over the consideration of temperature or by the method of cooling, the material will be transferred from its phase from one to another. So in such cases, there will always be increase in the hardness or strength of the material, and one such case is nothing but phase transformation hardening. Here what we do is, we are going to change the phase that constitute the microstructure of an alloy. So the best example here is transformation of steel from austenite state to the martensite state. So we are going to consider a constant combination of a steel here, whereas the temperature or the transformation temperature will be of a major focus that results from the phase of a steel from austenite to the martensite. So the detailing of all these type of hardening or strengthening of metals will be studied in the module of heat treatment of metals here. So this is the introductory part which is included in the module 1. So this covers the complete module 1 for material science 18 ME 34. Thank you.